Welcome to my course on functional programming principles in Scala. As the name implies, we're going to do quite a bit of Scala programming, but that's not the primary objective of the course. The primary objective is to teach you functional programming from first principles. You're going to see functional programs, methods to construct them, and ways to reason about them. You're going to find that functional programming is a paradigm that's quite different from the classical imperative paradigm that you know from languages such as Java or C. In fact, you can combine the two paradigms, and it's one of Scala's strengths that it provides a gradual migration path from a more concise Java-like language to full functional programming. But in this course, we are not going to be gradual. We're going to take a clean break. I'd like you to suspend for the time being most of what you know about programming and look at programs with fresh eyes. That way, I believe you'll be better able to absorb this new way of thinking, that's functional programming, and once you've done that, you'll also be able to integrate that back into your daily programming practice. In fact, Scala is a great tool both to learn functional programming from first principles and later on to integrate it with classical object-oriented programming. So let's get started. So I've talked about functional programming as a different paradigm. If you go back to the meaning of the word, in science a paradigm describes distinct concepts or thought patterns in some scientific discipline. In programming, we can distinguish three main paradigms. There's imperative programming, that's what you probably know from languages such as Java or C. There's functional programming, and there's a lesser known one called logic programming. Some people call object-oriented programming a paradigm, but in my mind it's really something that's orthogonal to the three paradigms here, in the sense that it can be combined well with both imperative programming, that's what is essentially the current state of the art, but also with functional programming or even logic programming. So let's review what imperative programming is as a paradigm. Imperative programming is really about modifying mutable variables using assignments, and those will be composed with control structures such as if then else, loops, break, continue, return, and so on. The most common informal way to understand imperative programs is as instruction sequences for a von Neumann computer. Von Neumann was one of the pioneers of the computer, built the first computer around 1945. So a von Neumann computer, it consists essentially of a processor and memory, and then there's a bus that reads both instructions and data from the memory into the processor. And what's important is that the width of that bus is about one machine word, so 32 bits or 64 bits nowadays. Now it turns out that that model of a computer has shaped programming to no small degree. There's a very strong correspondence between the memory cells of a von Neumann computer and the mutable variables in a programming language. Variable dereferences correspond then to load instructions in the computer. Variable assignments relate to store instructions. Control structures all translate into a sequence of loops. So that's all very well, but the problem is scaling up. We want to avoid conceptualizing programs just word by word. We want to reason in larger structures. That was the argument made by John Backus in his Turing Award lecture titled "Can Programming Be Liberated from the von Neumann Style?" It's noteworthy that John Backus was in fact the inventor of the first high-level language at all, that was Fortran in the 1950s. So more than 20 years later, he found that the traditional course of action of imperative programming had run its course, was running out of steam, and that something new was needed. And the new thing that he was proposing then was functional programming. So John Backus argued that in the end pure imperative programming is limited by the von Neumann bottleneck, which means that we conceptualize data structures word by word. If we want to scale up, we need to define higher level abstractions such as collections, polynomials, geometric shapes, strings, documents, and so on. And to be thorough, we need theories of these higher level abstractions, collections, shapes, and so on, so that we are able to reason about them. So what is a theory? In mathematics, a theory consists of one or more data types, operations on these types, and laws that describe the relationships between the values and the operations. So what's important is that a theory in mathematics does not describe mutations. A mutation means that I change something while keeping the identity of the thing the same. So for instance, the theory of polynomials describes the sum of two polynomials by laws such as this one here. Here we say to sum two polynomials of degree 1, we take the two coefficients of the same degree and we sum those coefficients. And there would be laws of all the other useful operators for polynomials. But one thing the theory does not do is define an operator to change a coefficient while keeping the polynomial the same. Whereas if we look at programming, imperative programming, one can do precisely that. One can write a class polynomial that would have an array of doubles containing the coefficients. One can then define a concrete polynomial p, and one can set the coefficient 0 of that polynomial to 42. When one does that, the polynomial p is still the same. That in mathematics simply is not available. It would detract from the theory of in mathematics, and in fact could damage this theory by breaking laws. Let's look at another example. Strings. So most programming languages have strings, and they would also define a concatenation operator. Let's write that plus plus here. And one of the laws for concatenation is that it's associative. So a plus plus b with parents to the left plus plus c is the same as a plus plus b plus plus c with parents to the right. But again, the theory does not define an operator to change a sequence element while keeping the sequence the same. This one actually some languages do get right. For instance, in Java, the type of strings is immutable. It also does not give you an operator to change a character in the string while keeping the string the same. So these were observations about theories in mathematics. What are the consequences for programming? Well, if we want to implement high-level concepts following their mathematical theories, we find that there's really no place for mutation. First, the theories do not admit, they don't have a mutation operator, and second, if we would add it, then it could in fact destroy useful laws in the theories. And that leads to a new style of programming where we say, well, we want to concentrate in defining these theories for operators which would in the end be expressed as functions. We want to avoid mutations, and if we are going to do without something, we want to gain something else. The things we gain is to get powerful ways to abstract and compose functions. So a style of functional programming means avoid mutations, get new ways to abstract and compose functions. In fact, there are two ways to look at functional programming, a restricted one and a more general one. In the restricted sense, functional programming just means programming without mutable variables, without assignments to those variables, without loops and the other imperative control structures. So it takes a lot of things away. In the more general sense, functional programming means focusing on the functions in a program. So in a sense, it gives you new capabilities to work with these functions. In particular, functions can be values that are produced, consumed, and composed. All this can be done in any programming language, but it becomes much easier in a functional language. So then we can also look at functional languages in a restricted sense or in a more general sense. In the restricted sense, then a functional programming language is one which does not have any mutable variables, assignments, or imperative control structures. And in the wider sense, a functional programming language is one that enables the construction of elegant programs that focus on the functions. In particular, functions in a functional programming language are first-class citizens. What does that mean? It means that essentially you can do with a function that you could do with any other piece of data. So you can define a string anywhere, you should be able to define a function anywhere, including inside other functions. Like any other value, you should be able to pass a function as a parameter to another function and return it as a result from a function. And as for other values, there will be a set of operators to compose functions into richer functions. So what are some functional programming languages? In the restricted sense, there are not many. There are some subsets, such as pure Lisp or Haskell without the I/O monad or unsafe performer I/O. There's an experimental language FP, that was the one that Bacchus proposed, and there's some domain-specific languages, mostly in the XML domain. So examples are XSLT, XPath, or XQuery. In the wider sense, we see the Lisp family of languages, starting with Lisp with prominent dialect, scheme, racket, and closure. The ML family that has SML, OCaml, F# as the most popular variants, Haskell, the full language, Scala, and also Smalltalk or Ruby. So you might be surprised to see the last ones in the list of functional languages, because they generally count as object-oriented languages. But since both of these languages have a construct of blocks, which are essentially first-class function values that you can pass around, I think it's fair to also adopt them in the functional family. Another example of that would be JavaScript, which has similar capabilities. So if we look at the history of functional programming languages, we find that they date back to almost the beginning of programming languages in general. The first functional language was Lisp, invented by McCarthy at the end of the 1950s. Then there was a lot of activities in the 1970s and 80s with ML, FP, Scheme, Smalltalk, Standard ML, reaching into the 90s with Haskell and Erlang. Later languages include OCaml 2000, Scala 2003, F# 2005, and Clojure 2007. So to find out more about functional programming, I recommend this book, Structure and Interpretation of Computer Programs by Harold Abelson and Gerald Sussman. The second edition appeared at MIT Press in '96. That book is an absolute classic when it comes to functional programming. Many parts of our course and also the quizzes are based on it, but we changed the language from Scheme to Scala. If you want to find out more about Scala, then I have to recommend my own book, of course. It's called Programming in Scala by myself, Lex Spoon, and Bill Wenners. It also appears in second edition at Artima Press 2010. And that's in a sense the standard language introduction for Scala and standard language reference. So there are many other books published about functional programming in general and Scala in particular. I only pick out 3 to recommend, but there would be many other choices as well. First recommendation is Scala for the Impatient by Kai Horstman. That gives a fast-paced introduction for people who already know Java well. The second one is the O'Reilly book, Programming in Scala. And the third one is called Scala in Depth by Josh Dürrith. As the name implies, that book goes quite a bit further than the other introductory texts. You can find links to all of these books on the course site. So if I open up the course site and go to additional resources, then I see the text, the links for all the books here. And quite a few of them are actually available online, either as the full text or in parts. Now I've given you a quick introduction to functional programming and why it matters. I've stressed that there are simpler reasoning principles and better modularity, but there's actually a third reason why functional programming is becoming increasingly popular. And that's because it's very good for exploiting parallelism on multi-core and cloud computing. To find out more about this third aspect, there's actually a video that I gave last year at the OSCON Java conference. The video is called Working Hard to Keep It Simple, and you get that also from the site. So you find the slides of the video here, and the talk you find here. I recommend that you go now to that talk to find out a little bit more about Scala, what its role is, what its purpose is, and why functional programming is important for parallelism and concurrency. After you've done that, you can come to the next lecture where we are going to do some Scala programming.